Okay, we're continuing on here. We're talking chapter 12, which is our first chapter about equilibrium. And again, as we've been talking about equilibrium having to do with those reversible reactions, where again, when it reaches equilibrium, what we're talking about is our rates of that forward direction equaling the rates of the reverse direction. We saw a couple of sort of equilibrium expressions that we could write. We have really the Kc, which is really just an equilibrium constant where we take the products concentrations over the reactant concentrations. Remember that we do use the coefficient from the balanced equation as the exponent. So again, if you had something like this, and we would write our Kc as c to the fourth and a to the second in this case. That is what's sometimes referred to as the Kc value when we're doing it all with concentrations, which is molarity. We also can, if we have gases involved, we could write a Kp expression. Works the same way, except that we're going to use pressures here. So it's really the pressures of our products all together, also divided by the pressures of our reactants as well. Again, we still use coefficient as the exponent when we're putting it in there for our partial pressures as well. The Kc and Kp values we talked about does not usually equal the same number or numerical value. They can, but in a lot of cases they will not equal the exact same numerical value. But they will tell you what we talked about just in general in terms of the equilibrium constant, which is if we have a large value of K, we would expect products to be present at equilibrium. Again, just taking a large number divided by a small number will get us a large number. If we have a small value of K, we would expect really the opposite sort of situation. We would expect reactants to be present. That's because we would have a larger value on the bottom, smaller value up on top is going to give us a small value. Remember that anything that is 1 and above is sort of considered, or above 1 is considered a large value of K. Anything less than 1 is considered a small value of K. K also does not have any units associated with it, so it is just a number. And the other important thing that we talked about last time as well is it really doesn't matter sort of what you start with in a reaction. As long as the temperature remains the same, the value of K will be a constant value. So as we talked about before, you could do a bunch of experiments for a particular reaction, and maybe on the first one you do all reactants, next one maybe you do all products, next one you got a little bit of everybody. Again, the ratio of products to reactants, as long as the temperature doesn't change, should always end up being the same ratio of products to reactants, and you will end up with a constant value for K. Temperature is the only thing that will change the value of K. And as we also talked about, we're talking about a comparison between the K value for that reaction, say at 25 degrees to K value at 45 degrees. In comparison of those two K values, they will be different because the temperature is different. We also talked about a way to go between these two K values, and that is the Kp is equal to Kc RT delta N. That's our Kc value. That's our Kp value. R is our gas constant, our 0.08206. That is our temperature in Kelvin. And also really important with this equation, our formula, as we talked about, is the delta N part. That's the moles of gas minus the moles of gas on the reactant side. So delta N is the moles of the products, gas molecules minus the moles of the reactants. And it's important to make sure that you do it that way, because if you do end up with obviously a negative value for that, it will affect obviously the math part of it when you do that formula. Any questions on any of that stuff we talked about last time? All right, so continuing on here, I think we also sort of touched upon this earlier, but just a reminder as well that we do not include everything in the equilibrium expression. There are a couple of things that will really not affect the equilibrium constant. And those two things are solids and liquids. So solids basically just kind of sit there, don't really participate too much in the equilibrium, and liquids concentrations typically are pretty constant throughout the experiment. So if we have this reaction here, we want to write a proper K value for it. We would include the CO2 as it's a gas. We would not include the calcium oxide or the calcium carbonate there, as they are both solids. And if we were writing the Kc for this, that would be the proper Kc expression, which is basically just our product there, which is the concentration of CO2. We would not include anything else, so our Kc would be just the CO2. Because CO2 is a gas, we could also write a Kp for this one. Partial pressure of CO2 would be, again, the only thing that would be included. So solids, liquids, we leave out of the expression. And that means, really, as we talked about last time, the only two things that get included are things that are aqueous and things that are in the gas state. So these two are, again, what we do include in our equilibrium expression. Questions on that there? And again, here you can kind of see, as we talked about, solids just kind of hanging out there, not really participating, although we may make more or less solids in the solid state as it becomes, really not participating, so not included in that expression. All right, so why don't you give this one a go? Okay, so let's take a look. So obviously in this case, as we talked about before, you want to kind of think about the information given to you. So in this case, it would make sense to calculate which one first, the Kc or the Kp? Should calculate probably which one? We should probably calculate the Kp first, as we have pressures given to us, right? So that would be the good move there. We really can't directly calculate the Kc because we have no concentrations given to us. We only have, again, those pressures. So our Kp in this case would be the partial pressure of NH3 times the partial pressure of H2S. Once again, that is a solid, which will not be included in here. In this case, each gas has that pressure, so we basically just pop that in there, 0.265 and 0.265. That is going to get us here, we'll call it 7.0 times 10 to the minus 2 as our Kp value. Any questions first off on that there? Maybe 7.02 here in this case. Now that we do have the Kp value, that's going to allow us to calculate the Kc's in that formula, where again, our Kp equals our Kc, a little RT delta N action. In this case, obviously, we just calculated our Kp. R is the gas constant, so we always have that 0.08206, or the 0.0821 is fine as well. In this case, we do have the temperature, and it is actually in the proper units. It's already in Kelvin, so we don't have to do much for that. So we do want to do our delta N in this case. So we're going to take the moles of our gas, which is on this side, of products, and that's one of each. So that's 2 minus 0. So once again, that is a solid. So that is going to give us an N value, our delta N value here of 2. At that point, I think we've got everything we need. I got like a 7.02 times 10 to the minus 2. Kc, 0.08206 times our 295. We're going to square it. We clean up a little bit there on the right-hand side. 0.08206 times 295 and a little squaring action. And this is going to get us about 586.0127. We're obviously going to take this to the other side and divide. So we'll take 7.02 to the minus 2 divided by that number. And there we go. And that's going to give us here a Kc of about 1.20 times 10 to the minus 4 in this case. Any questions on any of those there? Once again, here we see which is very common, which is usually those numbers are not the same, but once again, they can be. But they do tell you the same thing in terms of the equilibrium. They are both considered a small value of K as they're less than 1, which they both would then recommend or indicate that probably mostly reactants in this case, since it's a small value of K. Any questions on that calculation there? All right. Another thing that very commonly happens with equilibrium reactions is sometimes we do have to manipulate equilibrium equations. As you may know, not all reactions occur in like a one-step process. Not all reactions go directly from, say, reactants to products. It may be a result of multiple individual reactions that are added together or that occur. And one of the things that occur, for example, here is if you were to add these two equations together, anything that is on the opposite sides of the arrow that's the same will completely cancel out or reduce down if they're not the same number on opposite sides. And we will get everybody on the left-hand side of the arrow will stay there. So that'll keep our A plus B going to our E plus F. So this C and this C will cancel. This D and this D will cancel. Everybody on the left-hand side stays there. Everybody on the right-hand side stays there as well. And this would give us the overall reaction that occurs. We'll see this a little bit later on when we go backwards with something known as Hess's law, when you add a bunch of equations together, kind of similar to maybe what you've done with redox when you're kind of adding equations back, the half reactions and stuff like that, opposite sides cancel. We could also have a K value for this. And if we take the K value for that reaction, like normal, the K would be the concentration of E times the concentration of F divided by the concentration of A and the concentration of B. Now, we get that actually by not adding the K values together for each of those reactions. Reaction 1, we'll call it, in reaction 2. That's the K value for reaction 1. That's the one for reaction 2. But we actually get it by multiplying. So if we multiply these two K values together, the C's cancel, and that leaves us our overall expression that we have for the overall reaction, which is E times F divided by A plus B. So if you have multiple equilibrium reactions that you're going to add together to give yourself like an overall reaction, which occurs a lot and in a lot of different chapters that we come across, to get the K value for that equation that you added together and ended up with, you multiply the K values together. So super common error people want to make is they want to add those K values, but here you do actually multiply the K values. So if we have multiple, like I said before, sort of individual reactions, and you add them together, we multiply all the K values together to get the K value for the overall reaction. In this case, we only added 2 equations, so we multiplied 2 K values. If we added 4 equations, we'd multiply all 4 of the K values together to get that overall one. So it doesn't really matter how many you have, you just multiply the K values together. Another very common thing that we do is sometimes when we're adding reactions together, we don't need the reaction the way it's written. So what I mean by that is we don't need the reactants where they are. We actually need them on the product side. And then we don't need the products on where they are. We actually need on the reaction side. So very commonly, we reverse a reaction. And when we reverse a reaction, basically our reactants become our products become our reactants. So what happens to the K value is you actually take 1 over the K value when you do that. So if we have this reaction here with a K value, don't worry too much about the number, but we have this K value to end up at 4.63 times 10 to the minus 3. And this reaction here is basically just the reverse of it. We just basically flip the reaction around the other way. And we would take 1 over K, and we would end up with 216 as the K value for the reaction on the right. So if you need to reverse a reaction, you basically take 1 over the K value. You do not change the sign, which again is a super common error people make. They just like, oh, I reversed, I'll just change the sign of it. So it actually ends up being 1 over the K value. It's also really important that when you do see a K value, this number here, for example, is specific for exactly the way that reaction is written. Whatever's on the reactant side, whatever's on the product side, just like 216 is exactly for this reaction, how it's written, what's on the reactant side and what's on the product side. So it'd be incorrect for me to say 216 is the K value for this reaction the way it's written, because it actually should be 4.63 times 10 to the minus 3. Yes, sir. So this would be a situation, we'll see an example coming up soon, but this would be a situation where maybe you're given an overall reaction and you want to know what the K value is for the equilibrium constant for that reaction, but you're not given like individual equilibrium concentrations or pressure, but you're given a bunch of other little reactions, and you have to kind of manipulate those reactions until they add up to the reaction you're looking for, and then you have to obviously multiply the K values together and keep track of everything you did to it. So it'll be a situation like that. We'll see. Other questions? So these are, again, two very common ways that we manipulate equations. Sometimes we have to reverse it. And again, like I said before, sometimes we need to add the equations together. A couple other things that we do with these type of reactions or equations that very commonly happen. Let's just say we have A plus B goes to C plus D, and the K value is 10. Now, let's just say I needed this reaction not to have like just one A, but I needed like two A's. So if I needed two A's in this situation, I essentially would have to multiply the entire equation by 2. And when I do that, that would give me 2A plus 2B goes to 2C plus 2D. Now, what does that do to the K value when I do that? So when I take this reaction here, we'll call it number 1, and I write the equilibrium expression, the Kc is C times D divided by A times B. Now, if I take this equation here, number 2, and I write the equilibrium expression for it, K would equal concentration of C squared D squared divided by A squared and B squared. So what I did to the first equation was multiply the entire equation by 2. What happened here in terms of our equilibrium expression as I did that? As I multiplied by 2, my equilibrium expression now becomes squared. Yeah, so in this case, I would have to take K and square it because I multiplied by 2 in this case. By the way, if you multiplied by 3, you would take the K value and cube it. Yeah, multiply it by 4, take it to the 4th power. So if you need to multiply an equation by a common number, what you do to the K value is you take that K value to the power of that number you multiplied by. Multiply by 5, you take the K value to the 5th power, and so forth. Any questions on that? So that also is a very common sort of manipulation of the equations that we do. Now, let's say the other thing that we do, which is maybe we're not multiplying by a common number, but maybe we actually need to divide by a common number. So let's just say, for example, here that we were actually starting with that second equation. And obviously that would be 100. So let's just say we were starting with this equation, 2A plus 2B goes to 2C plus 2D, K equals 100. Now, again, let's just say that we did not need 2 in this situation, but this was the equation that was given to us of A. We just need 1 of A. So if we just needed 1 of A here, we would actually divide this entire equation by 2. When we do that, we will end up with A plus B goes to C plus D. And again, what we're essentially doing in this case is we're starting with this equilibrium expression, and now we're ending with this equilibrium expression here. And as we go from right to left in this case, it goes from the squared to not being squared. So basically what we do is we would actually take the square root of 100, and that would give us an equilibrium constant of 10 in this case. So if you have to divide by a common number, you basically take the root of that common number. So if I divided by 3 all the way across, I would take the cube root of the equilibrium constant. If I divided by 4, I'd take the fourth root of it, and so forth. So those are, again, two very common ways that we manipulate equations. If you multiply, you take the k value to the number you multiplied by. So if you multiply by a number, take that k value to it. And if you divide by a number, take that k value root, basically, to that number. And those are really the four ways that we manipulate these equations. Reverse it, multiply by a common number, divide by a common number, and then ultimately add these equations together. And as I mentioned before, this is a situation where you have multiple individual sort of equations, but you're looking for what is the k value of the overall equation that was maybe given to you. Any questions on that? So let's just say we had a really simple one here. So if we had like a plus b goes to c plus d, and k is 5, and then c plus d goes to go e plus f. K is equal to 10 in this case. All right, and we're looking for this overall reaction, sort of what is the, not that one, put it like that in E. E plus F. We are looking for, again, what is the K value for that reaction. So really what you want to do is just kind of go through each of the individual reactions, just make sure everybody's on the correct side and see if you have to reverse something or multiply by something. So clearly here, I can see A plus B is on the correct side, so that's good. I'm not really going to do anything to that one. And that would be me. Obviously, my K is here since I didn't do anything to it. Now, actually, let's just change this just a little bit here just to make us do something here. So let's just say this was E plus F goes to C plus D, K, we'll keep it at 10. All right, so now I look on the other side, and I need E and F on the right-hand side, but here that I just changed it, obviously, here. And if that was originally given to us, it's not on the correct side. So I would have to reverse that reaction. So what I would have to do in that case is reverse that reaction to get everybody to the correct side. Once again, when I reverse that reaction, I'm going to take 1 over the K value is basically what happens when you reverse that reaction. Now, if I did this correctly and I add these together, these C's should cancel, these D's should cancel, and that will leave me A plus B goes to E plus F. And again, that is the equation that I'm looking for. Now, in terms of the K for this guy, we'll call this K1 and K2. We would take K1 times K2. So that would be 5 times 1 over 10. Again, we're not adding these together. We're actually multiplying them together. So we'll take 5 times 1 over 10. And that will give us a 0.5 as our K value in this particular example. Any questions on that one? Not too hard to pull it. All right, so why don't we try one where you have to do a little bit of manipulation here. Should have some, I think. All right, so up on top is the equation we're looking to figure out the K value for. You want to figure out the K value based on the information below. So take a few moments, rearrange those equations if necessary, keep track of what you're doing, and then see what you end up with for your K value. Okay, let's take a look at it. So when you're doing these, and again, we'll see it again later on in the semester, They used to teach you this in 200A, some stuff like this. But when you're adding equations together to try to build an overall equation, you just want to kind of keep it really simple. You just want to think about just getting everybody to the correct sides and making sure you have the right amount of everybody. So if I were to approach this, I would look on this side and go, all right, obviously E and F is on the left-hand side. When I come down here, the only equation that has E and F in it, it's on the right-hand side, so that's not good. So I know for sure I need to reverse that reaction and put it on the other side. I also don't need one E or one F. I actually need two. So I know for this one, I need to reverse this reaction and also multiply by 2, basically. So those are the things I have to do to that equation. And if I do that equation, that will give me 2E plus 2F, again, reversing the reaction and also multiplying by 2, 2C plus 2D. Now that I did all that, I have to remember how that affects my equilibrium constant value. Because I reversed it, I got to go 1 over the equilibrium constant. I also multiplied by 2, which means I got to take the equilibrium constant and square it, right? So those are all sort of the adjustments that you did to the equilibrium constant. You got to kind of keep track of it. All right, that puts all my E and F on the correct side. Obviously here, A and B are on the right-hand side, and this equation has A and B on the left-hand side. So I do need to reverse that equation. And I only need one A and B, and that means I don't really have to do anything like multiply or anything like that. So I'm just going to simply reverse this equation. And again, because I reversed the equation, I got to go 1 over the equilibrium constant because I reversed it. At this point, I used both equations, which means I hopefully did it right. I have nothing left. So I'm going to add these together. Once again, anything that's on opposite sides of the arrow that's exactly the same can cancel out. It's kind of like the arrows are equal signs, like subtracting it off to the other side. Or it can reduce down. It doesn't necessarily have to always completely cancel out, but it can reduce down. So if you had like 4 on one side and 2 on the other, you could subtract it and end up with 2 on the other side. So here, these are going to completely cancel the C's. The D's will completely cancel. Everybody on the left-hand side stays there, so 2E plus 2F. Everybody on the right-hand side stays there, A plus B. I now have built basically the correct equation that I'm looking for. Any questions on that there? Because we ultimately added these equations together, if I call this K1 and K2, the K value for this equation would end up being K1 times K2. Again, we're not going to add, we're going to actually multiply the adjusted numbers here. So if we take 1 divided by 20 and square it, that is going to get us 0.0025. We take 1 divided by 100, 0.01. So we'll take 0.0025 times 0.01. That's going to get us a K value for the overall reaction, 2.5 times 10, a lot of zeros there, 1, 2, 3, 4, 5, negative 5 as our answer. Any questions on that there? So that's kind of the approach that you want to take. Just kind of keep it simple, get everybody to the correct side, make sure you have the right amount. The key with this one is to keep track of everything you did to those individual equations so you could adjust the K values accordingly. Let's try one more maybe. All right. So for this one, what is the K value for the bottom equation based on the K values of those two equations up there? Just want to kind of build the equation on the bottom from the other two in this case. By the way, we just have 2 in these examples. You could have 3, 4, a bunch of individual equations. So it doesn't really matter how many you have. Just want to kind of take the same approach, just kind of build, put everybody on the right side. So obviously here I got N2. Really, this is the only equation that N2 is sort of in. So it is on the correct side, but I do need 2 of them. And in the top equation, I have a half. That means I really do need to multiply this guy by 4 there will get me 2. So I have to multiply that entire equation by 4. And if I do that, that's going to get me 2N2 plus 12 divided by 2 is 6H2 to the other side there, 4NH3. And since I multiplied by 4, remember we're not going to multiply the K value by 4, but we are going to take it to the 4th power. So again, a very common mistake. People want to always like multiply the K value by that. You do not. You got to take it to the power. Now I got water here on the left-hand side, and this again is the equation that has water in it, and it is on the left-hand side, which again is good. But I don't need 2 waters like it is there. I do need 6. So that means I'm going to have to multiply this guy by 3, that equation. And if I do that, I will end up with 6 waters. Goes to 6 H2s plus 3 O2. Again, the only thing I did was multiply by 3, which once again means we are going to take the K value and cube it basically to the 3rd power. I'm clearly out of equations at this point, so if I didn't screw it up, there's a 50-50 chance. We should end up here with our right equation. We want to cancel out anything that's on opposite sides, so that's the same. I think in this case, it is only the H2, which are on opposite sides. Now, everybody on the left-hand side in each of those equations stay there. So that's a 2N2 plus a 6H2O. Everybody on the right-hand side of the equation, 4NH3 plus 3O2. That should be the overall reaction we are looking for there. First off, any questions on that there? Once again, if we just want to number these 1 and 2, the K value for this one is going to be K1 times K2. Once again, not adding them, but multiplying those. We also need to adjust each of those K values based on what we did to them. So for the first one there, we're going to take 411 to the 4th power. And that's going to give us something like 2.85 times 10 to the 10. And we're going to go 0.345 and cube it. And that's going to give me 0.04106. We're going to multiply both of those together. And if we do that there, looks like a lot of numbers. Too many to count. We'll go 1.17 times 10 to the 9 in this particular case. Any questions on that there? So again, this is a very common thing that we do. When you do see a K value, once again, it is specific for the temperature it's at and exactly how that reaction is written, what's on the reactant side, what's on the product side. So if you need to manipulate a reaction, you have to manipulate the K value. If you have to rewrite it, flip it around, or anything like that. Any questions? All right. So again, this sort of talks about what we just went over. If we do not include solids and liquids in our equilibrium expression, once again, it is specific for the temperature. And we can add equations together, which we will add the K values. If we have to multiply an equation by a common number, we take the K value to that common number. And obviously, as we saw there, if we divide, we're going to take the K value to the root of that common number. All right. So as we also touched upon last time, doesn't really matter where you start with in terms of these equilibriums. As long as that temperature remains constant, you will always end up with that same ratio. So there's many different sort of positions of the equilibrium constant, but they will all come to the same value as long as temperature remains the same through all those runs. You'll get the same ratio even if you don't have the same amount of products and reactants in each run, but that ratio of products to reactions will remain the same. Another really important thing with equilibrium is a side note here of a different letter that popped in, and that is the reaction quotient. And the reaction quotient is the letter Q. So if you see Q, it represents the reaction quotient. The good news is the reaction quotient is basically calculated the exact same way you calculate K. So we calculate K by taking the concentration of our products, obviously with the exponents, to our reactants. And that means Q is calculated the exact same way. You take your products divided by your reactants. You do the exact same thing you do for K, which means you take the coefficients, they become your exponents and everything. Now, you may be saying, why do I need Q if it's calculated the exact same way as you calculate K? The reason that we use Q is really kind of for two reasons. First off, you may be given concentrations of everybody in a reaction or an equation, and you may not know if you're at equilibrium. So you could calculate Q and determine whether or not, based on your Q calculation versus your K value for that equation, if you're actually at equilibrium. The second thing that Q tells us is if we are not at equilibrium, it will tell us which way that reaction has to go to reach equilibrium. Does it need to make more products to reach equilibrium? Does it need to make more reactants to reach equilibrium? So if you calculate Q and it is greater than the K value, then the reaction is not at equilibrium. And in order to reach equilibrium, it has to go to the reactant side. So if you think about an equation, reactants to products, if you write Q on the left and K on the right, opposite of where this points is where it needs to go. So it needs to make some reactants. Yeah. Q uses the stoichiometric values as well, so you do use the coefficients and all that. The main difference is really that you have concentrations of everybody, and you really don't know if you're at equilibrium. You don't know if these are initial concentrations, if they happen to be equilibrium concentrations. So you really don't know. It's kind of a straight up type Q type question is a straight Q type question is pretty much that. Are you at equilibrium? And if not, which ways has to go to reach equilibrium? And that's really what Q is for. Is it calculated identical to how you would calculate the equilibrium constant? In these type of problems, you would have the K value given to you, and you would calculate Q and compare it to the K value that's given to you to make that determination if you are at equilibrium, or if not, again, which way it needs to go to reach equilibrium. That also means that you can really only calculate Q if you're given the concentrations of everybody. So you have to be given the concentration of all the reactants and products in a problem in order to calculate Q. Obviously, if you're just given reactants, there's no way to calculate Q. You don't have to worry about it. But if you are given pretty much the concentration of everybody in the equation, probably the first thing you should always do is calculate Q to help you determine that. And it'll be an important sort of step as well in a later calculation that we'll talk about to help you determine if you're kind of doing the calculation right as well. If you calculate Q and it does equal the K value, then you're really at equilibrium at that point. It's not going to go either way. It's obviously has reached equilibrium. If you calculate Q and it's less than K, you are not at equilibrium. It needs to go towards products to reach equilibrium. And that is the way the reaction will actually basically proceed. So if Q is greater than K, basically the reverse reaction is going to happen. And if Q is less than K, then the forward direction is going to happen. Obviously, as Q is equal to K, it will be at equilibrium. It won't really go either way. It's happy the way it's at. Any questions on that there? So like I said, there's kind of two types of places we use Q. Most commonly in just a straight up Q type question, I call it, which is pretty much that's usually what you're asked. Are you at equilibrium? And again, which way it needs to go. And that's because in some problems, they may not tell you, hey, these are equilibrium concentrations or anything like that. They may just tell you, hey, these are the concentrations of everybody. And you might want to know if you are at equilibrium or not, and that would affect how you do a calculation, for example. So let's take a look at one. Why don't you give it a go? At the start of the reaction, there's 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, 6.42 times 10 to the minus 4 moles of NH3 in a 3.5 liter vessel at 375. The Kc for this is 1.2. Is this system at equilibrium? And if not, which way does it need to go to reach equilibrium? So take a few moments there, calculate it up. This is what I would call a straight up Q type question, basically. Okay, so let's take a look, see how you're doing. So in this case, we're given the moles of everybody. We're also given the volume. Hopefully, you can get molarity from that, which is moles per liter. So we really do have the concentrations of everybody here. And like I said before, this is sort of like a straight up sort of Q question. It usually will ask that question, are you at equilibrium and which way it needs to go? So that should automatically trigger for you that Q is what you want to calculate here. So once again, Q is calculated the exact same way as we would do K. So this would be the concentration of NH3 squared divided by N2. We're going to use the coefficients just like we do with K, and that'll be H2 cubed. And once again, the idea here is we don't know if these are initial reaction concentrations, equilibrium or not, and that's really what we're trying to determine here. If we knew they were equilibrium, we could just throw it in there, and we could get the equilibrium constant, which we already have given to us, but we would know it should equal 1.2. So we do need some concentrations here, so we'll calculate those. So N2 would be the moles, 0.249, divided by the volume here, 3.5 liters. And that's going to get us here, 0.249 divided by 3.5. Looks like we'll call it 7.11 to the minus 2 molar. Concentration of H2 would be its moles, which is 3.21 times 10 to the negative 2 moles, divided by our 3.50 liters. 3.21, make sure you are using your exponent button. Negative 2 divided by 3.5. 9.17 times 10 to the minus 3 molar. And lastly here, our NH3, going to go 6.42 times 10 to the minus 4 moles divided by 3.50 liters. 6.42 to the minus 4 divided by 3.5. Going to get us a 1.83 times 10 to the minus 4 molar. Any questions on those calculations there? Once again, I think we talked about it, but just in case, right? Exponent button. Yes, make sure you're using it properly, right? Make sure you're using your exponent button, not the inverse log or anything like that. Shift log. That is wrong, by the way, if you're doing that. Q is equal to our NH3, which is 1.83 times 10 to the minus 4 squared, divided by our N2, which is 9.17 times 10 to the minus 3, and our H2, 1. Not that. Gotta do that one backwards there. So I got H2, which needs to be cubed there. I'll pop it in the right spots. There we go. All right, so N2, 7.11 times 10 to the minus 2. H2, 9.17 times 10 to the minus 3, and we do need to cube that one. All right, 1.83 to the negative 4 squared divided by 7.11 to the negative 2, hit equals, divided by 9.17 to the minus 3, and we're going to cube it. That's going to get us a 0.611 as our Q value. Now that we have the Q value, we want to compare it to our K value that was given to us, which is 1.2. And we could hopefully see in this case, Q is less than K, right? So the first thing that tells us is the system is not at equilibrium. And in order to reach equilibrium, got to go the opposite way there towards products, right? So we'd have to make some products there. Oops, to reach equilibrium. Questions on that? Obviously, if you just think about the ratio, right, products over reactants, if Q is less than K, you need some more products, right, to bring the top number larger, bring the overall K of Q towards K, right, to build it up. Any questions on Q? All right, calculate it. Yeah. So again, I would say very commonly, this will be the type of problem you'll see it. We will see Q pop up though in the next type of calculation we're going to talk about as well. So it's kind of two places you could do it. Once again, you could only calculate Q if you have all the information for everybody in the equation. If you do not, there's no way for you to possibly calculate it, and you don't have to usually worry about it. So let's talk about the major calculation of the season here, which is equilibrium constant problems. Now, when we solve for equilibrium concentrations, we are usually given initial concentrations, and we actually have to do a calculation to figure out what the equilibrium concentrations are. We typically do what is referred to as an ice table. Now, ice table stands for initial, change, and equilibrium. Now, you might have come across an ice table in 200A, probably not based on most people that are teaching it. Unless you took me, then you've seen it. But you might have done it when you did limiting reagents. Sometimes people will teach limiting reagents using ice tables. But if not, we'll talk about how to do it here. So the idea here is we are going to try to figure out how the reaction is changing based on the initial concentrations. So let's say we have an equation such as A plus B goes to 2C. We'll go with the K value of 10, for example. And let's say that initially here, we have an initial concentration of A of like 2 molar, and for B, and we'll go with 3 molar, why not? And that's all that's given to you, and that usually means initial concentration. See the little knot on the bottom there? And what we're looking for is what is the equilibrium concentrations of everybody. So in this particular case, we have just the initial concentrations. We have to do this ice table to figure out the equilibrium concentration. So starting with I here, initial concentration of A is 2 molar. Initial concentration of B is 3 molar. And I would say in most cases, if you are not given any information about the product side, it is definitely safe to assume you have 0 of it. So if there's nothing mentioned about any of the products, you could safely assume that is 0. And that is the I from our ice table sort of line there. Any questions on that there? Now, the change part is really the important part of the table. It ultimately is what we're looking to sort of figure out and solve for. And we usually represent the change in these ice tables as X. So X is typically the thing that we use to represent the change. So if we just think about this reaction, and if we only have reactants given to us, which way should this reaction probably be heading? Should it be heading in the forward direction or the reverse direction? Which way should it go? It is going to be the forward direction. Remember that there is no possible way for the reverse reaction, which is products to reactants, to happen because you have no products, right? You can't make that happen until you make products. So because we have no products in this case, it is probably safe to assume that this reaction is going to initially start heading in the forward direction. We're going to take some of our reactants and we're going to make some products in this case. With that being known, we would expect our reactants concentrations to increase or decrease with time. It's like a 50-50 shot. What do you think? It should decrease, right? Because if the forward direction occurs, as we talked about, I think in some earlier examples, those reactants have to come together to make products, which means the amount of reactants should start to decrease. The amount of products should then start to increase. And we represent that in the ICE table with minuses and pluses. So whatever is decreasing is minuses. Whatever is increasing, obviously, is pluses in this case. Now, we do use the x, and this would be minus x, and really it's minus x because we also need to, when we do the change, which is a super important part, we have to take the coefficients into account when we do that. So since the coefficient for A and B is 1, it's basically 1x. You don't usually write the at 1, so we just call it x. But when we get to the product side, it should be increasing, so that's going to be a plus. Coefficient is 2x in this case. If you do not use the coefficients in the change part, you basically just did the wrong mole-to-mole stoichiometry relationship. That is basically where the stoichiometry comes into play. That is why it's sometimes taught with limiting reagents to use an ICE table. Basically does the mole-to-mole relationship for you and the stoichiometry for you. Super wrapped up into one move there. So it's really important to make sure coefficients get used with the x's. Yeah. So again, using our coefficients. Now that we have our change, we get to E, which is our equilibrium, and all we're going to do basically is just bring everybody down. I can get rid of the molarity here and just call it 2 minus x, 3 minus x, and 2x. The 2 and the 3 are still molarity, and just keep in mind, but just so there's not some letters in the way of our calculation, I'm just going to get rid of the m, but it's, again, still molarity in this case. First off, any question on the ICE table, how we did it? So once we have this, really the goal of this table is to figure out what x is and what the value of x is. Now, we could do that because we have the equilibrium constant given to us. And we could write our equilibrium expression for this, which would be, we'll assume these are all aqueous. K would equal the concentration of C squared divided by the concentration of A times the concentration of B, and that's going to equal lucky number 10 there. So, is your question? Yeah. It would have been 2x. Yeah, exactly. Yeah, so these are all ones here, but in your example there, if that was a 2, then the 2 would be popped there and obviously carried down as well. Yeah. And that's really, really important because if you don't have those coefficients in there, you're essentially doing the wrong calculation. And really what you're missing is the correct stoichiometry, the mole-to-mole relationship type of calculation. Other questions? All right, so let's get rid of those there so we don't confuse here. And bing, and bing. All right, so what we do now is we take our equilibrium line pretty much, and this is where it varies from what we did with limiting reagents. We're actually going to put everybody in the equilibrium line into our expression. So what that's going to give us is 2x, and we still need to square it, divided by our 2 minus x and our 3 minus x in this case, and that is going to equal 10. At this case, it's fun math time, yes. So part of the fun math is there's a few different ways you could solve these. One of the ways that's common that we do solve these type of problems is with the quadratic formula and the quadratic equation. If you're not familiar with the quadratic, it looks something like this. If it writes ax squared plus bx plus c equals 0. And that goes to x is equal to minus b plus or minus the square root b squared minus 4 times a times c divided by 2a. Yeah. And if you've used quadratic formula before, you get how many answers when you do that? You do get two x values, yeah? And in most cases, only one of the x values are going to be good. Since we're running out of time, I'm not going to solve this particular one, but let's just talk about some other things here. Once you use something like this, for example, and you solve for x as one way that you could solve this type of problem, you will have two x values. So we'll have two x values at this point. By the way, you do need to do a little factoring right on the bottom here, right? In and out, in and out. Sounds good for dinner, but you got to do all that right and get it all set up into your quadratic formula. And once you do solve for the x values, what you're going to do is check each of those x values by going back into the equilibrium. And let's just say hypothetically, and this is not right at all, I'm just making up these numbers. Let's say 0.5 was one of the x values. And let's just say we had 3.5 as the other. Again, made up values. All right. Now, what we would do with each of these is check to see which one is the good one. Now, hopefully you know these x values represent all the x values we see in our table. And if we were to take, for example, this one, and I put it into here, that would mean for A, I would have 2 minus 3.5. I believe that is a negative 1.5. Doing the math in my head, I hope, molar. Can I have a negative concentration? No. So we would not want to use this x value if that happened to be what you ended up with, because it would give us a negative concentration. You can have a not have it. You cannot have a negative concentration or a negative pressure. So one of the x values, if you use the quadratic, will lead you to a negative value in that equilibrium, and that would not be the right one. That would, by default, mean that that guy in my made-up number would be the correct x value. We would then go back to this table, and for all those x values, we would put in, obviously, the proper number, and that would give us our equilibrium concentrations for everybody in this particular case. First off, any questions on that there? Reminder that if you use the quadratic, you could get two positive numbers like we just saw there. You could get a positive and negative number. You could get two negative numbers when you solve for it. You do want to test it by putting it back into that equilibrium line. And as long as it does not give you a negative value, you're good with that one. The other one should probably give you a negative value. Any questions on that? Last thing I'll say to tie it into Q of what we talked about earlier is if we were given the initial concentrations of everybody, so let's just say we were given like initial amounts and we didn't have zero up here in this table, right? So let's just say hypothetically we were doing this problem, get rid of all this, right? And let's just say instead of not having any C, let's just say that we were given a value of C initially. And let's just say it was, I don't know, 5 molar. So now I have 5 molar, right? At this particular time, I'm not really sure which way it could go, right? Because obviously I got some products, I have some reactants, could be heading in the forward direction, could be heading in the reverse direction. This would be a situation where you're doing equilibrium calculations that you would want to calculate Q. And if you found that Q was less than K, then you're okay because it should go to the product side. But if you calculated Q, in this case, let's just say you calculated Q and it was greater than K, that means the reaction to reach equilibrium needs to go to reactant side. How would that affect my change line? That would mean that the reaction's heading not in this direction, right? But it's heading in this direction, which means my product actually would be decreasing and my reactants would be increasing, right? So it would change the pluses and minuses if you were in that situation. So that is the second place where Q could come into play. Not too often that happens, but you could have an equilibrium problem like this where it's probably a good idea to calculate Q if you do have everybody given to you, just to make sure you're doing your ice table correctly. I would say probably 99 times out of 100, you could probably roll autopilot to the product side, but there are a few times where you might need to calculate Q just to verify. And once again, we could not calculate Q in my original example here because we were only given reactants. We weren't given anything about the products, so there's no way to calculate Q. So you don't have to worry about it in that situation. But if you are definitely given concentrations for everybody, you should, before you get into your equilibrium calculation, calculate Q to verify which way it's going. Yeah, they typically, on these problems, give you K. Otherwise, you would have too many unknowns to try to solve for. So yeah, you definitely will have to use K in these problems. Questions on that? All right, we'll lay it up there for today.